Can I see myself? Yep. Welcome everyone. Thank you for coming, both in person and virtual. And I have the pleasure to introduce Matt Devlin, a scientist in the P3D group at Los Alamos National Laboratory. And today he's going to talk to us about nuclear fission, current issue and open questions. And this is actually going to be the last lecture this week about nuclear fission. So it concludes Fission Week. And welcome our guest. Thank you.
Yes, I can see you. Okay. I have to figure out where to stand. Good afternoon. All right. Good afternoon. My talk today is on nuclear fission. You already had a couple other talks this week, and I was going to try not to duplicate too much, but to say a few random things that are fairly recent with respect to fission studies. If you have any questions, please feel free to interrupt. If someone sends something into a chat or something, just tell me the question. So first, maybe I can go. It's not toggling for me now. There we go. Fission. This is the introductory side, which should be redundant from what you've seen earlier this week. Fission is when a large heavy nucleus, like an actinide, breaks up into two pieces. It's neutrons and gamma rays, they're fission fragments. Timescales are all relatively short. For perspective, so sort of a physics perspective, if you give it enough energy, all nuclei above 10 can fission. It's not just actinides. It's just that the threshold for them is quite high in most cases, and it's not relevant to most applications. Among the actinides, you can go off stable with in-beam experiments and look at fission and fission fragments. And one sees a particular pattern. Asymmetric fission, like in the actinides, plutonium and uranium, is not universal. There are numerous competing symmetric branches for different isotopes. At higher energy, it's all symmetric, it's all statistical. And in that sense, it's easier to understand theoretically and also less interesting. Asymmetric fission is its own thing. And that includes spontaneous fission and neutron-induced fission, low energy typically. Just as some words about terminology. When the nucleus breaks up, when the actinide breaks up into two pieces, we have primary fission fragments. These decay by gamma rays and neutrons. They then beta decay later, and those are the secondary fragments. And those give you the cumulative yields for mass yields and such. If one looks at a generic distribution of fission fragments for asymmetric fission, it's like this. This is a calculation. The truncation in the lower and upper corners is not real. The calculation just stopped there. One sees two bands of fission fragments, all neutron rich. Also on this plot are the shell structure, closed shells for the nuclei, of course, the stable nuclei as well. Closed shell nuclei tend to have lower Q values or lower ground state energies, so that you can gain the most energy by going to them. You don't actually see that high mass peak hitting the middle of the closed shell. There's a reason for that. It's a little bit opaque, but recent work, and I'm not going to go into that in detail, but recent work has suggested that, in fact, it's not just the dipole shape that matters. There are quadrupole minima that are different in place. They're a little bit northeast of the closed shell around 132, and that the actual minimum there is between the two. So both effects matter. That's a little bit more complicated than I want to get into today, so I'm not going to go into that. But I do want to show you a couple other aspects, let's put it the right way, of fission. On the top plot here is the mass distribution from spontaneous fission of californium, thermal fission of 235, and thermal fission of 239. You notice that the heavy peak doesn't move so much between them, but the light peak moves a lot. Something about where the heavy peak is in the mass chart and the shapes involved and the nuclear physics involved keeps that steady, whereas the light one moves much more quickly. There's some other plots on here too, but we don't need to go into those in detail. I had put the next plot in to discuss some details with Akpol deformation issue. But because I want to keep this relatively straightforward, I'm not going to go there. This is the generic plot of what happens when you get into a fission fragment. Neutrons decay first, losing a little bit of spin, but not much. Gamma rays then decay quickly to the ground state band, and then give off a lot of E2 excitations. But what about energy? Total energy of the fission fragments is the Q value for that particular mass split. And you can take an average over all the mass fragments for that. Plus the neutron energy if you have an incoming neutron. It's spontaneous, that's a 0. And that gives you total kinetic energy and total excitation energy separately. If you imagine just at the point of scission that the two nuclei are touching each other, you have two charged particles right next to each other, which will accelerate away from each other. The energy is proportional to Z1, Z2. If you measure the total kinetic energy of fragments, you get a result that looks a lot like what's called viola scattering, after a professor at Indiana, Vic Viola. And you can see there's two terms in this equation for viola scattering. One is proportional to Z squared of the compound system, divided by a to the third, and the common amount. This is simply a reflection of the Z1, Z2 kind of energy production mechanism for TKE. The raw TKE before you emit any particles is largely Coulomb energy. And momentum is always conserved, of course, linear momentum. If you look at the TKE versus mass, you see that for asymmetric fission at all energies, that the more symmetric ones have more TKE, and the less symmetric ones have less. That makes sense if it's Z1, Z2, because the maximum of Z1, Z2 is when Z is equal to Z2, right? There's a spread, of course. It's not just that one issue. And on this plot, we bring up another issue, which is that this is as a function of incoming neutron energy. I think it's 235. The lower energies in the top two plots, and then higher energies in the bottom two plots. As the energy goes up, the amount of symmetric fission grows in. One can look at that more directly. I'll keep going the wrong way. More directly in a plot like this, which shows you the two mass peaks. This is a pre-neutron emission mass. Stefano made the point when we were discussing earlier, in parallel to the comment about fission fragment mass of the heavy fragment not moving when you go from uranium to plutonium very much. As you go up in energy, it's also true that the light ion loses more than neutrons. So it moves faster as a function of neutron energy coming in. That doesn't show up here because this is an extracted pre-neutron emission mass based on a model. But this one has the fit as you go up in energy for the symmetric mode, which is quite broad, and at least the upper, the heavier fragment, asymmetric mode, you can see how it changes. All this, sure.
What are the axes of this?
This is mass on the bottom. So this is the mass of the two fragments, and it's forced to sum to the total. So it's pre-neutron emission, and then probability in percent. It's a log plot, so you can see down the tails. And as an aside, it's not been discussed a whole lot recently in literature, but there are other fission modes that come into play, and various ones that have been proposed and no one actually believes anymore. Here's two modes. There are at least 4 that actually happen. And people will occasionally do fits with little extenders on the sides for some of the rare modes. There's also ternary fission where you can have 3 particles come out. Typically, the third particle is light. There's scission neutrons where the neutrons are stuck in the middle when the two things break apart. All of these things are, generally speaking, low probability. If you're worried about applications, you don't need to know that sort of stuff. But that's where these other features come in. And my talk is actually structured as a series of topics that are disconnected. So this is the first break to the next topic. This is what I work on, so it's the thing I know the most about. I think you were going to talk earlier in the series from the historian from Los Alamos.
Yeah.
He probably did not mention to you the first publication in the Los Alamos Report Library. It was actually LAMS1, they've changed the thing now, it's LAUR. And it was on the prompt fission neutron spectrum as guessed in 1943. The answer is actually a bit wrong. They have the peak at 2. The answer is a little bit lower than that. It's typically a Maxwellian. And it's typically a Maxwellian shape because the fission fragments lose the neutrons. Fission fragments are highly excited and they just evaporate them off. The level density is high and it's just all statistical. So that's what you expect to see. That is actually used in the assumption of fission. They knew that in 1943. And by the way, Hugh Richards was the chair of the department in Wisconsin when I showed up there as a grad student. I didn't know about this one. He actually came in and sat in an office across from me for a while too. And I didn't know the connection at all. So let's. I'm stuck. There we go. Yeah, I mentioned this already. There's a Maxwellian shape there. There's another term for it called a Watt spectrum. The Watt spectrum is slightly more complicated, has a slightly different shape for various reasons. It was developed in the 1950s, but it looks Maxwellian. That's the gross shape and everything else is the detail on it. And when I start showing results, I'll show prompt fission neutron spectra divided by the Maxwellian so you can see the features, right? Why do people still care? It matters for criticality. It matters a lot. One of the issues in nuclear data at Los Alamos and elsewhere is that if you're trying to model a complex system with a lot of multi-physics going on, the nuclear physics is the stuff that you can actually hope to measure with known precision and eliminate that as a free parameter in fitting various systems. Typically, we talk about fitting nuclear data like prompt fission neutron spectra or neutron cross sections to critical assembly data, which are very relevant for the fast region. It's also very relevant for fast reactors. I'm not going to talk too much about the lower energy region because that's more of an older topic. But at the higher energy region, this is an example of the prompt fission neutron spectrum for a range of energies. This is an older plot, so it's ended at 7 on there. I just wanted to show you what it looks like when it's divided by a Maxwellian. You have incoming neutron. This is the prompt fission neutron energy on the x-axis, the probability of a neutron being in that bin on the y-axis, and each panel is a different incoming energy, and they're listed on the sides. You can read them. And they're compared to various versions of NDEF at the extremes of the two distributions. As you go up in energy, other things start happening. And you can see these effects in the prompt fission neutron spectrum. All right, good. And I have a movie to show you. Unfortunately, they don't let me choose the speed in PowerPoint. So I'll let this sit there for a minute while you try to think what could possibly be making these shapes. And I'll show you something else and come back to it. If you look instead at the cross section of fission for a given actinide, this happens to be a fissile isotope. It goes up the bottom there, it doesn't have a threshold, but the cross section has steps in it. Each step is second chance or third chance fission, so-called, and those are actually fit separately there, so you can see them. And you get a total. And on the right-hand side, you see something else, which is it's labeled pre-fission here, but it's pre-equilibrium neutron emission, which I'll go into in a second. Here's a plot that explains it. First chance fission is when the neutron comes in, or in spontaneous fission, it's all first chance. The neutron comes in and breaks up into two pieces. If the neutron coming in is high enough energy to allow a neutron to evaporate from the compound system, and it does so, that would be second chance fission. What you actually see, as you saw in the last plot, is a combination of those two distributions with each other. So the prompt fission neutron spectrum would be two distributions. Even more energy, you get third chance fission. And if the first neutron that comes out, there's enough energy in the system for a neutron to come out at all, and if it comes out before it's shared all of its energy, it comes out with too much. Then that's called pre-equilibrium emission. So for pre-equilibrium emission, one way to think about it is it was actually inelastic scattering that resulted in fission. So some energy is deposited by the neutron and some is taken away by the neutron. Okay. And since I can't stop the movie, I'll show you a different energy region here. This is third chance, down to the third chance fission. There's both the pre-equilibrium component, which is that large rise at the highest outgoing energies. And as you go into second or third chance fission, if that nucleus actinide fissions from second chance or third chance, it has lost the energy of the neutrons that left. So it is now a relatively cold fission system. So its prompt fission neutron spectrum comes in a little lower. That shows up as a bump that moves across in the movie. I'm actually going to go back and see if I can see if you can see it now. There's a bump, a wave that sort of goes across. That's the second and third chance fission being seen in just the neutron distribution, not in the cross section. What else happens? Commonly, people look at a property for prompt fission neutron spectra called the average energy. The average energy of all the fission neutrons, because that tells you most of what's going to happen in something. And if you plot that as a function of energy, you see a dip for second chance fission and a dip for third chance fission in 235. We measured that. These are our results. It's published. In 239 on the right-hand side to you, the dip for third chance fission that NDEF wanted to see wasn't there. That's relatively new. I get a kick out of telling managers at the lab that neutron emission spectra at 14 MeV in plutonium were wrong. You can ask yourself why people didn't notice that, but it's a small effect, right? And there's other ways to fit a model to a data set that has that type of neutron in it and hide this effect. But now that you know it's there, you can get the right answer. Why might it not be there? The most obvious answer is there's no fissioning system left. Just by the time you get that high up, cross sections for 1 and 2 are so large that there isn't much third chance fission that can possibly happen, so it doesn't change the average much. And that's probably the right answer. The evaluated database for the fission cross section of 238 plutonium, which is a couple direct measurements, which are hard to do because it's a short half-life, and some surrogate reactions. It suggests that almost the entire reaction cross section is going to fission. There's no N3 yet, which is consistent with this sort of picture. It's just fission so often that nothing else happens, even before you get to third chance. I'm going to change topics again, so if anyone has any questions on that. Not, we'll go. If it lets me. Right. There we go. Total connected energy, which I mentioned before. This is just a plot that explains a couple things that are sort of simple. The total kinetic energy of plutonium is on the left, as measured in a 2E kind of system. There's also the plot says this work is a work by the Oregon State group led by Walt Loveland. And they broadly agree, both experiments were at Alamos. It's a log plot, so all you should take away from it is that there are 2 slopes as a function of energy. And you can look at the total amount of energy that's lost. As you go from, say, 1 MeV, you're below 175 MeV total in 2 fragments. At 10 MeV, you're at 173. So that's 2 something MeV difference, right? 171, yeah, it's like 171 and 170. So it's a little over 3, sorry. On the right-hand plot, I've showed a recent measurement of newbar. Plutonium as a function of instant neutron energy. This is published on the archive, but the paper itself is not yet out. This is an interesting measurement. It was done with Kinu. V sub mu is prompt newbar. If you look at the details of the plot, it actually has little dents down at the second and third chance fission barriers. That's not actually been seen in Nubar before. You kind of expect to see it. The second system's colder, but remember you've also added neutrons to kind of balance each other. So it's a very small effect. This is the only data set that actually shows that. But look again at the energies. If I go from 1 MeV to 10, I've gained, that's 3.1, that's 4.2. I've gained a little over 1 neutron. The average energy of every neutron is kind of flat. I showed the plot earlier. It's around 2.5, 2 MeV or so, right? So I've gained 3 MeV. Yes.
I'm guessing the answer is no, but is there any way to experimentally discriminate between like a pre-fission neutron and a post-fission neutron? Is there not?
You certainly don't have time resolution to do that. Now, if it's a pre-equilibrium neutron, it has typically a distribution in angle and energy that's different, and you can tell that way. It's remarkably flat. We actually have a paper on what it looks like.
So you probably could do it event by event, but you could like subtract it. Sort of.
Yeah, you can see the result in a histogram, but you can't do event by event. Right. As far as the second chance one, it happens to be low energy, but you're measuring it in the distribution of energies. So you can't do that either, right?
Right.
Anyway, my point was that the gain in energy by the neutrons matches the loss in TKE over this region. This all makes sense. The excitation energy is being lost by neutrons and gammas, but the neutrons take away the TKE first, right? Is that true? And that's another plot with the same left-hand panel, but the right-hand panel, I show you the uranium-235 equivalent plot from a different publication. Notice that it goes down the same way. There's a fit to it. There's earlier data shown on there. And this is a Loveland plot with the big data points. The early data is from Dana Duke at Los Alamos. If you look carefully at the x-axis, below 1 MeV, TK is going in the wrong direction. Why does it do that in uranium and not plutonium? Maybe it's just wrong. But there's some old data. This is about 30-year-old data from uranium TKE. Same group, 2 different gases in their chamber, but it shows the same. Yeah. It seems to be real. It's been measured twice, and you see a gain in the first MeV for uranium-235 and TKE. And I just told you that it should be going down, and it's going down everywhere else. I didn't promise I'd solve every problem I was going to bring up, and I don't know the answer to this. But it's interesting. My next topic, I won't have much to show for, but I have quite a few words because it's complicated. There's been a lot of interest lately in how angular momentum is generated in fission. What do we know? We know that all fission has a substantial amount of angular momentum. Spontaneous fission in every isotope. There's no zero angular momentum fission events. The average amount of spin per fragment is on the order of 5, 6, 7, it depends. If you bring in more angular momentum with a charged particle reaction or a high energy neutron, you can get more. But even spontaneous fission with nothing coming in has angular momentum. So the fission process itself must make that. The question currently is how. There are a couple different models. I can only show one of them, but this is one from Jürgen Randrup at Berkeley, and it has an analogy in heavy ion reactions, which people have studied for decades. Heavy ion reactions, you send one heavy ion into another with enough energy that they merge, and then they go off into, in this particular example, 2 separate fragments of masses that are similar to the original nuclei. They traded some nucleons, and they spent some time in the same place, but then they fissioned again. They do it in such a way that we don't use the word fusion fission. They call it pre-equilibrium because it's a different type of process and it's modeled a little differently. But in those models, they worked hard on figuring out what the angular momentum should be because they could measure it. And they came up with a system in which there were a number of ways two fragments coming away from each other could be given angular momentum, could give each other angular momentum. Remember, with californium or any spontaneous fission, you're starting off with 0, and angular momentum is conserved, so you have to end up with 0. But each fragment has to have some, so that they have to cancel each other in total. So there's orbital angular momentum and intrinsic. The debate about intrinsic angular momentum has been a more recent thing. Intrinsic meaning the angular momentum of the nucleus itself. Orbital is relative to each other. And the reason I don't have a lot of slides about this is that it gets a little tricky to explain, right? But these modes here, where you say wiggling, where they both set out the same spin and wiggle against each other, or bending, where they start on opposite spins and go off with more orbital angular momentum. And there's tilting as well, which can give you a mode that's 2 things in a row, 2 aligned angular momentum, and twisting. Note that tilting has them both aligned. So that can't be a system that starts off at 0 spin or close to it. So it doesn't count for fission, for spontaneous fission. It could count for neutron-induced fission. The other 3 taken together have to be in this model, but that's the only way you're generating angular momentum. So you have to imagine that these things happen. It depends on the mass of the fragments. And you would naively assume that the intrinsic spin of the fragments on an event-by-event basis would be correlated. Turns out they're practically not. Practically not correlated with each other at all, but the total is kind of fixed. So the mechanism gives you a certain amount, and it adds up to 0 in total with the angular momentum added in, but the intrinsic parts are not correlated between the nucleons. It's just statistical, somehow. What happens when things fission? Nucleons have to choose which side to be in, somehow. And as it's fissioning, they can perhaps move back and forth. The more moving back and forth there is, the more room there is for a model like this to make some sense, right? However, in all of these cases, and in this model, everything is in plane with the fission axis perpendicular to the fissioning fragment axis. It's built into the model. It's not a feature that falls out of the model. It's done beforehand. This makes sense because that's how you expect a nuclear reaction to go. If you send a charged particle next to another one and then scatter, the angular momentum of the system is perpendicular to the plane the reaction happened in. It could have happened in this plane or that plane. It doesn't really matter. But in that plane, that's why people publish results for scattering as a function of theta, the angle off the beam axis. And don't worry so much about phi because any phi is equivalent, right? Relative to the fission axis, that's the picture that people use. It turns out that other calculations that have been done recently suggest that it may not be in plane. And how that happens is a debate. It could be a mistake in the calculation. It could be something that's missing, of course. It could be something that was actually brought up. Let's go back. Here. The authors of this here had an explanation for why that upslope happened. The only thing that changes between 0 and 1.5 MeV in nuclear structure is typically that that's when you reach the pairing gap. In a nucleus, nucleons can be paired to other nucleons in the nucleus itself. When that breaks, you open up a lot more levels. If you look at the level structure of uranium-238, for example, at 1.7 MeV or so, you all of a sudden get a whole bunch of new bands. Before that, below that, it's much sparser. That's simply a pairing phenomenon. So we know pairing is real in nuclei. Pairing is most often talked about in superconductors, but it's the same general idea. These particles are paired, so they have to be matching in angular momentum. And of course, in a nucleus, they're pretty much only rotating. They have to be equal and opposite. Matched. That's a pair. In superconductivity, they call it the Cooper pair. Seen the term repeatedly for nuclei, but it's different because angular momentum matters a lot more for nucleons than it does for electrons and superconductors. So one model in which you can get things out of plane is if paired nuclei during fission go to opposite fragments. So you break a pair. It's not on in Jurgen's model at all. In fact, it's a little hard to find. But that was the explanation, pair breaking, in the structure of it, was the explanation given for this effect. But remember, nobody sees it in 239, so I don't know. And obviously, I should have drank less coffee this morning, since I finished what I have here. This is a nuclear engineering audience, though, so I want to give you one more plot. I showed you the linear scaling up of nu bar as a function of incoming neutron energy. The widths go up too. So all the moments go up as a log plot. All the moments go up as well as the nu bar average, like on that plot. So any questions?
So what's the estimate of how much energy it takes to break a pair?
In a nucleus, it's about 1.5, depends on the structure of it, maybe 2 MeV. There are various ways to make the estimate. It's been 30 years since I was in a graduate class in nuclear physics and I've forgotten. But that's kind of where you are. You can see that experimentally in the accidents.
So maybe a prediction of that, if it is actually nuclear pair breaking, would it mean that at high incident Newton energy, we would expect the element to become more isotropic?
Yeah.
Okay. We can check.
Yeah. There's another aspect of that with correlated neutrons from the same nucleus.
Yeah.
Because as you go up in higher energy, you get more nucleons, more neutrons coming out, and they're more likely to come from the same nucleus just because there's more of them.
Yeah.
So you can look at correlations between them, and that tells you something about the fission axis. So if the axis is out of plane, you might see something. But it's tricky. All these things are tricky.
You mentioned that there's a real dip in neutron multiplicity at the second chance fission barrier of plutonium.
It's small.
That's not like a detector threshold effect because the pre-fission neutrons are just less energy. It's actually
Where we go?
fewer neutrons.
Go too far. I'll show the effect to the size of it. No, there's no detection efficiency threshold there.
Okay.
Right. This data here to get the nu bar, they've detected everything they can with their threshold. It's liquid scintillators, right? So they have a threshold below which they don't get it, but they fit that with an Maxwellian to estimate the number that's missing. And that's part of the uncertainty that folds into it. So the only thing that happens as you go up there, if you have a threshold effect, you're really expecting to see it when the energies are lowest. Right? And we showed the plot where the energies don't really change. Right? All right, went out of percentage views, what happened? If I go back in and go wrong. So. Yes.
So going back to PFNS, it seems like to get that right, obviously more measurements are needed to, especially really differential measurements. So like, for example, I've been looking at the good experiments where there's fragment neutron correlations and you have, time of flight energy spectra of the neutrons. But the fragment measurements are pretty uncertain on the order of like a handful of, mass numbers and they have no measurement of the proton number.
Mhm.
So it seems like there's now new like ion chamber technologies that can do much better measurements of fragments and get mass and charge numbers pretty precisely. Are there plans to do a measurement with that sort of ion chamber and something like KINU?
Yeah, that's Stefano and Nathan were discussing possibilities there. And there's European measurement as well that's being planned. I find this subject a bit amusing in the following sense. At higher energy, when you can accelerate particles and you have charged particle beams where you don't have to worry about how many events you make, people have done these sorts of very complicated measurements for a long time. Mm-hmm. And the reason is it's easier up there because the particles all have enough energy that you can tell them apart, right? What makes this hard is that fission fragments have 1 net MeV per mass unit, right? And that's an area that detectors technology is not quite so good.
So for example, if we wanted to just stick a spontaneous fission source in there, we would not be getting as precise measurements of A and Z as if we have like a, if we put it in the.
Yeah, so a beam of uranium-238 gives you, and you just getting off a sample. So all you do is have a Coulomb interaction, and it then fissions. That yield of fission fragments is perfect. You get N and Z, right? As long as you gave it enough energy to stay with. And you have to guarantee a different reaction didn't happen. You didn't have the right compound system, but people try to take that result and then go say that what the uranium fission should be if it's spontaneously fissioned, or if it neutron fissioned, if you had a neutron target, right? Or it borrowed a neutron from the target you have. And the issue there is theoretical. You have slightly different reactions, so you go to slightly different states in the fissioning system. The spin doesn't match, spin and excitation energy don't match exactly. So you have to figure that out and increase your prediction. There are people at Berkeley and Livermore who say they know how to do that. There are people elsewhere that say we're not so sure that works. There's a history of it working and not working, but it's getting better. And I think this is a solvable problem. And that's a much easier experiment to do in principle. Right. But someone has to do a hard experiment to get the same results so that everyone agrees that yes, that works. Right. But measuring the details like prompt fission, neutron spectrum, neutron number in those methods again is it could be complicated and someone might have to work hard. There is a plutonium new bar that was done with a circuit measurement at Texas A&M a few years ago. It's in print by a Livermore group, and it agrees. The error bars are just bigger because there's an uncertainty to how they extract the information they want. You can't get rid of because you're doing a circuit reaction. You can't beat down the theory too much. Any questions from the chat?
Not yet, but I'm gonna check now. If you have any questions, please type in chat, or you can also just raise your hand, and we can take questions now. So yeah, go ahead and type in the chat. Otherwise, are there any other questions here? Or maybe people type.
I have a general question. You showed a lot of very complex, detailed phenomena, rarest measurements, right? Can you comment on the ability of theory and theoretical codes to predict those complex behaviors?
I can't make a comment on that without annoying somebody. There are recent calculations that were published in recap was published material from Seattle, which are supposedly complete. For the first time, he used supercomputers and a theoretical model to make fission happen on its own in the calculation. That had never actually happened before in the calculation view. The model I showed you with the twisting and stuff, that has to start with the fissioning system. Right? That's an improvement. The first principles kind of calculating stuff is showing progress. The reason it has taken so long is just that the calculations are so complicated that not only do you need faster computers, you need to figure out how to simplify them. And this particular calculation, and people running it think they have a way to simplify it enough that they can get a result. Whether the calculation is right or not, I have no idea. More often, you use something like FRIA or CGMF, which is built on experimental results and fit to them. So you're modeling what the next case should be. There's another model in Europe, Annabella Tudor's, that has so many parameters that she'll fit anything. Right? But as long as you're consistent, at least it's predictive. You can go to the next case, right? There's this really bizarre politics, which I've never quite understand, but it turns out, at least a few Russians, one in this country, who have opinions on what the prompt fission neutron spectrum is, and they know. So I think someday you'll get an answer. We don't have that yet.
Yeah. Just a follow up to, you mentioned some of the details of these phenomena. They're not that important in application, right? If it's a sub% effect, then you're looking for an application that doesn't really matter. Can you comment on how good does the theory need to be, to model fission in an application sense, right?
Yeah, well, it depends on the actual application, but I did show the plot with the average energy, but it was wrong at 14 MeV. That's not a small effect, right? That matters. So we do the measurements to find those cases. We look at the fine details to learn more about the fission process. And one of the motivations for doing that, and this is the motivation for the surrogate reaction technique too, is that if one starts worrying about minor reaction lines, those measurements are even harder, right? So if we can fix the models so that the extrapolation to the next thing over makes sense, that's one way to approach the problem. If we can do a surrogate reaction and convince ourselves we can extract the right information and make the right prediction, we've solved that problem. And in a lot of cases, the minor reaction lines are not necessarily a small detail. There are applications in which they matter. And there are people interested in some of those properties. So there's a connection there, but you're entirely right that I didn't discuss ternary fission in detail because I'm pretty sure that's not related to anything anyone wants to hear about.
Somebody here.
Yes.
So kind of like reversing that question, specifically thinking about more phenomenological models like CGMF, is there like a prevailing intuition for what models that go into that are the most efficient or the most that have the most issues, sort of?
Yeah, the people developing it have some opinions on that, what they worry about. There's a corresponding code from Los Alamos by Toshihiko, BOH, or EOH, or whatever it's called this year, that's being developed to address some of those issues, right? The thing about CGMF and EOH is that they know the fragment structure. They have that built in. So you can look at the properties of fragments explicitly, right, in CGMF. Whereas Frye tradition did not have that. So you have to add that on. It's got average properties. Right? So the codes are a bit different in that sense. And that's something that, at least at Los Alamos, they think matters for comparisons to experiment.
There is a question in the chat, and I think it is a very general question, like a summary, which is, what is the main problem with nuclear fission? Meaning probably, what is the main open question of the one you presented today, or even other ones? What do you think? I think it's a subjective.
Yeah, that's a good question. I would say the biggest issue is understanding the mechanism enough that you can calculate off the ones you're looking at, right? There's a tendency in experimental science in general, and physics in particular, to always be looking under the light lamp, right? Because that's where the light is. My keys have to be under the light because I can't see over there, right? And in terms of physics measurements and other science measurements, that translates as doing the experiment just a little bit better than I just did. We're doing the same type of experiments that other people are doing, that sort of thing. This detector does X, therefore I measure X. And our methods at getting the mechanism of fission out have not quite worked out yet. So is there something we could be doing to fix that? Or do we just need to, is the problem correctly understood? We just have to brute force it. I don't know. But once you know the mechanism of fission, you could, in principle, reliably calculate Neptunium-238 or whatever you wanted to do. And the result will be good enough and trustworthy enough that DOE and their good sense wouldn't give you money to measure it. Right? That's the best answer.
And what kind of experiment do you think would be needed?
Well, for that, I can only think of the ones on the lamppost. Sorry.
No.
Keep doing what we're doing.
Yeah.
Right. Obviously, measuring the fission fragment axis matters. So I think that matters. And then looking at the fragment, at the products with respect to that axis. That's brute forcing. Right. It's not something brilliant we do.
I have a final question. I don't think there is more in the chat. But I have a question about this plot here, the TK versus lumbar. And does it mean because it's decreasing with the incident energy? Does it mean that the two fragments, as you said at the beginning, there is less electrostatic repulsion as you go up? So somehow the distance between the two fragments?
No, this term P is not prior. But this is after information.
Okay, so this effect here is because of infinite emission? This is
Yeah.
just bumps of infinite emission, like a RICO effect?
As you go to other fission fragments, of course, you change the Q values. So you could, in principle, change the total TKE, but you change slowly. You lose one or two more neutrons over the whole blob, and the blob just moves a little bit, so that's a slow-moving object. Thank you.
Thank you.